Okay, so let's recap a little bit where we were. Okay, so we first introduced the idea of topological spaces, and topological spaces have to it's the most abstract concept that you can have of a space with points and just the neighborhoods of points. And within the space of topological spaces, okay, you can now select topological spaces which have collections of smooth charts on them. And those define for you what are called manifolds. And the advantage is that once you have these smooth charts, then you can start to do things like calculus. You can do things like differentiation, integration. You can put vectors and tensors on a manifold and so on. And then among manifolds, okay, we saw that so of course manifolds allow you to choose metrics, choose tensors, but there's no specific tensor that is picked out by a manifold. If you now pick out a particular type of 0-2 tensor called a metric, then the space becomes a metric space. Okay, so a manifold plus a 0-2 tensor on that manifold gives you a metric space. Okay, and once you have a metric space, this will allow you to define notions like curvature, which we will do probably in the next class. So topology is based on this idea of continuity. Okay, manifolds are based on the idea of smoothness, and metric spaces introduce more structure to manifolds. They allow you to take things like dot products of 4 vectors, and so they could also create isomorphisms between vectors and dual vectors. And also, metrics allow you to now define distance measures for infinitesimal displacements. Okay, so if I have a displacement of coordinates, you can now associate a distance with that displacement in coordinates. Okay, this is not something that you can do when you don't have a metric. There's no natural notion of distance when you don't have a metric. Okay. Also on manifolds, we've seen that you need to impose additional structure if you want to compare tangent vectors at 2 different points on the manifold. And that additional structure is that you have to impose a connection. Okay, you have to impose a connection gamma, which allows you to parallelly transport vectors from one point on the manifold to another point along some particular curve. And what we've seen is when you go to a metric space, that is when you have a particular metric, then there is a unique connection that is picked out, which is torsion-free and metric compatible. Okay, and we defined those concepts earlier. I'll just recap those now. Okay, and this unique torsion-free metric compatible connection. Okay, sorry, torsion-free metric-compatible. Okay, this is called a Levi-Civita connection. So in general, when you just have a manifold, a connection on a manifold allows you to parallelly transport. Okay, so if you have a vector at some point P on a manifold, and if you want to transport it to a point Q, in general, the tangent space at P and the tangent space at Q are completely different vector spaces. But once you define a connection, it allows you to parallelly transport this vector V to a vector V prime at the point Q. So the connection allows you to connect one tangent space to another along some particular curve. Okay, so our definition of a geodesic on a manifold, not on a metric space, but just on a manifold, is that we define a geodesic as a curve on the manifold such that tangent vectors to this curve are unchanged under parallel transport. Okay, so that means that if you have a curve, okay, and the tangent vector to the curve here is V, and I parallelly transport this V over here, okay, then the difference between this parallelly transported V and the tangent vector to the curve at this point is 0. Okay, that's what we mean by a geodesic. Okay, that is, the tangent vector is unchanged under parallel transport. So I parallelly transport this tangent vector, I get this V prime. The tangent vector at this point on the curve is already some other V double prime. If V double prime and V prime are the same vector, okay, then you say that the tangent vector is unchanged under parallel transport. So we can of course write this using the affine connection that we defined earlier, this derivative. So it's basically the statement that the change in V along the V direction is 0. Okay, so this is for an infinitesimal change. And if this is true at all points along the curve, then the curve is a geodesic. Okay, so this definition gives us the straightest possible curve on a manifold with a connection. Okay, so this allows you to define a notion of straightness. Okay, tangent vectors are parallelly transported to themselves. Okay, so the tangent vector is unchanged under parallel transport. So in a particular coordinate patch, okay, this equation del v is equal to 0. We've seen that we can write it using in some coordinate patch, where in the coordinate patch you're using coordinates x mu, okay, and your curve is some x mu of lambda. So the curve x mu of lambda, these coordinates x mu of lambda along the curve should satisfy this equation. Okay, this is the geodesic equation in a particular coordinate system. Okay, but the rules that geodesic follows don't rely on any particular coordinate system, right? This rule is coordinate independent. This way of writing it makes it manifest that the rules are coordinate independent, right? Because this operation of del we've seen is defined independent of any coordinate system that you choose. Okay, and so this notation makes it apparent that this definition of a geodesic is not dependent on a particular coordinate system. Okay, but in some particular coordinate system, you can write the geodesic equation in this way. Okay, in a coordinate patch. Okay, it may not be defined over the entire manifold. Might have to switch coordinates as you move from one coordinate patch to another. And here the tangent vector is v to the curve. Okay, so I can write the tangent vector as v as some coefficients v mu partial x mu, and these coefficients v mu are dx mu d lambda. Okay, so this defines vectors which are tangent vectors to the curve in this coordinate system. So now if you solve this geodesic equation, okay, so if you solve this, okay, the solutions that you get will be some x mu of lambda. Okay, so given some initial conditions, okay, these are second order differential equations, so you'll need two initial conditions, okay, for each. So maybe, for example, you need x mu lambda initial and x mu lambda final. Okay, for each value of mu, you need to specify basically the initial point and the final point. Okay, so for example, I could specify this is the initial point, this is the final point. So I give you the coordinates of this point. That's giving you all the x mu's at lambda initial. I give you all the x mu's at lambda final. Now you use this equation and find for me the straightest possible path connecting P and Q on the manifold. Okay, and that straightest possible path is defined once you tell me what the connection is on the manifold. Okay, and remember, the manifold doesn't come with a connection. This is additional structure that has to be imposed on a manifold. Okay, so if you solve these with some initial conditions, it gives you the geodesic, which is a curve which parametrically we're expressing as x mu as a function of some parameter lambda. Okay, so this is what you're finding. Okay, so lambda is basically your sort of some interval on the real line, and you're mapping it to points which have coordinates x mu. Okay, on this manifold. So now, obviously, one thing that you could do is you could eliminate lambda, okay, and you could just find a trajectory, okay, on this manifold. So you don't have to think about the parameter lambda anymore. You could just think about the set of points, okay, on this manifold, okay, as defining a curve. So there are, of course, many other curves which will give you exactly the same set of points. Okay, there are other curves which will give you exactly the same set of points. These are really basically an alternative ways to parameterize the same curve. Okay, so for example, supposing instead of using the parameter lambda, I had used the parameter lambda square. Okay, then I might traverse this curve a little faster or slower. Okay, depending on, let's say, whether lambda is between 0 and 1. Or if it's greater than 1, right? So I will traverse the curve at a different rate, but I'll cover the same points. Okay, if I use a different parameter. So basically, there are many possible curves which cover the same points on the manifold. Oops. There are many possible curves which cover the same points on the manifold, which have just different choice of parameterization. Okay, so we really want to think of all of those as being the same curve. So our condition of this straightest possible curve, okay, is perhaps too strict. Okay, because here actually what our notion of straightest possible curve was we demanded that the tangent vector stays exactly unchanged, okay, for a straight curve. But it's not necessary for the tangent vector to be unchanged. What we really want is that when we parallelly transport the tangent vector here, okay, so let's say that you have a curve and this is the tangent vector at this point is v double prime, the tangent vector here is v. Now I parallelly transport v to this point, okay, and we don't really need v when it's parallelly transported to be exactly the same as v double prime. It just has to be parallel, okay, to v double prime. That's sufficient, okay. So again, there's no notion of magnitude here. Okay, there's no notion of the size of the vector, but all we need is that it's the change in V. Okay, the change in V under parallel transport along the V direction. Okay, all we need is that that change itself is just proportional to V. We're not really demanding that it's zero, but it's just proportional to V. This is sufficient to define a straight curve. Okay. So our geodesic condition can actually be more relaxed than just saying del V is equal to 0. Okay, we can choose this relaxed condition. Okay, as defining the geodesic. As we will see, this choice, okay, this alternative choice is equivalent to choosing exactly the same curve, okay, as we had obtained before with the condition del V is 0, but with a different parameterization. Okay, it has a different parameterization. So the demand that we're now making is that the change in the tangent vector V under parallel transport along the V direction, okay, is proportional to V. We're not saying the change is 0, rather we're saying the change is proportional to V. This proportionality constant F is not really a constant. It's a number at a point on the manifold. But as I move to a different point on the manifold and I look at the condition for parallel transport here, okay, this number F could change. Okay, so the only condition that we require on F is that F is some smooth function on the manifold. Okay, it's some smooth scalar function on the manifold. So F belongs to these smooth functions. So this proportionality constant can vary at different points along the on the curve. So this F just has to be a smooth function. Okay, smoothness is just so that you have well-defined notions of differentiability. Okay. So this alternative choice of defining a straightest possible curve using del V is equal to Fv, okay, this also gives you the same sort of geodesics with a different parameterization. That's what we'll show next. Okay, in fact, this is what I've assigned to you as an assignment problem. Okay, so let's show this. Okay, so this gives the same curve that you would get with this condition. Okay, except with a different parameterization. Okay, so let's see how to do this. Okay, so let's take this condition del V is equal to Fv. Okay, in a particular coordinate system, what we've seen is tangent vectors can be written as V mu partial x mu, and V mu is dx mu d lambda. Okay, so let's work it out in some particular coordinate system, and then the geodesic equation. You can show that so the del V, okay, in some particular coordinate system is this. Okay, these are of course coefficients of some vector. Okay, so this is along the partial mu direction. Okay, so the left hand side is this times partial mu. Okay, and the right hand side, okay, you can easily convince yourself then is F, which is some F at different points x times V coefficients, which are dx mu d lambda. Okay, so this is what you have in a particular coordinate system. Okay, so the equation is modified from before. Okay, so you now have this new equation, slightly modified equation, where you have a non-zero right term on the right hand side. Now the point is that we can show that it is possible to change this parameter lambda, okay, to some other parameter lambda prime. And when you reparameterize the curve in a particular way, okay, so first let's just see what happens under a general parameter change of parameter lambda prime. Okay, so under the change of parameterization to lambda prime, okay, for the same curve, so this x mu, which is as a function of lambda, we now express as a function of some other lambda prime. Okay, where lambda prime and lambda are related. Okay, so there's some function which takes you from lambda to lambda prime and vice versa. Okay, so so the tangent vectors, okay, to the curve when I reparameterize and now I make it a function of lambda prime, the tangent vectors, I'll call them V prime. Okay, the tangent vectors will change, okay, because the rate at which I'm traversing the curve changes. So these are V prime mu times partial x mu. So these are the new tangent vector coefficients. Okay, and V prime mu is dx mu d lambda prime. Okay, it's no longer dx mu d lambda. Okay, so these are the new tangent vectors. Okay, So how are these new tangent vector coefficients related to the old tangent vector coefficients? Well, v prime mu is dx mu d lambda prime, but that I can write as using the chain rule. It's d lambda prime times dx mu d lambda. Okay. So in other words, it's d lambda by d lambda prime times the old vector coefficients. Okay. So so our new vector coefficients, our new tangent vector coefficients are related to our old tangent vector coefficients by this transformation. Okay, this is just a number at each point along the curve. Okay, so it's a different number possibly at each point along the curve. Okay. Okay, so now this is the assignment exercise, which I'm not going to work out. Okay, but what you're supposed to do is show that if we choose lambda prime, okay, to satisfy a particular equation, that is, if you show that lambda prime satisfies some particular equation like this, that is d square lambda prime by d lambda square is f times d lambda prime by d lambda. Okay, and you replace lambda in terms of lambda prime, okay, in this equation, then what you will find is that this equation, the original equation, which I've labeled as A, this equation, okay, which has some term on the right hand side, in terms of this new parameter lambda prime, okay, gets recast into this form. Okay, d square x mu d lambda prime square plus gamma mu nu rho dx nu d lambda prime dx rho d lambda prime is 0. Okay. So, and this equation we've already seen before, that is with the new parameterization. That is, now that we've switched parameterization to this lambda prime, now with this new parameterization, the tangent vectors are the ones which satisfy this equation, which is del v prime is 0. Okay, that is, you've gone to the parameterization where the tangent vectors are no longer changing under parallel transport. Okay, so even though you started with a curve where the tangent vectors can change under parallel transport, okay, that is, they can change proportionally to themselves. Now what you find is that if I reparameterize the curve, I will now get back my original rule of a curve where the straightest possible curve where the tangent vectors do not change under parallel transport. Okay, not even by parallelly to themselves, they just don't change at all. So it is always possible to find this reparameterization. Okay, so the parameterization lambda prime of the geodesic that recasts it into this form. Okay, this form of B, which is in a particular coordinate system, it's the original geodesic equation that we wrote down, or in a coordinate invariant way, you can write it like this. Okay, so once you find that new parameterization, okay, and you can always find this new parameterization starting with any parameterization. Then you get what is called, this new parameterization is called an affine parameterization. Okay, so this affine parameterization is one in which the curve satisfies this equation. Okay, and the parameter lambda prime is then called an affine parameter. Okay, and it is always possible for any geodesic to find such a parameter such that the geodesic equation can be cast in this form. All right, any questions here? Okay, so the other thing is, suppose you have an affine parameter lambda prime. Okay, so suppose you already have put the geodesic equation in this form by choosing an affine parameter lambda prime. Then it's easy to see that if I change lambda prime to some other parameter lambda double prime, which is related to lambda through some linear relationship like this, lambda double prime is equal to a lambda prime plus b. Okay, then you can easily see that if I replace lambda prime by lambda double prime here, since they're linearly related, all I will do is pull out a factor of a square over here and a square over here, and so I'll get back the same equation in terms of lambda double prime. Okay, so I'll get back exactly the same equation with lambda double prime. Okay, so if I reparameterize my curve, my affine parameter to another affine parameter where I rescale by a and I add a constant b, okay, then I will get back exactly I will get back exactly the same form of the geodesic equation using the parameter lambda double prime. So where a and b are some constants. Okay, so this allows me to transform from one affine parameter to another affine parameter. Okay, but Now I can't have a general transformation. The transformations are more restricted. Okay, that is, they're linear transformations of my affine parameter. So this reparameterization, this restricted set of reparameterizations is called an affine reparameterization. Okay, so there's not just one affine parameter. There's an equivalent set of affine parameters which are all related by these kind of linear transformations. Okay, yeah, I'll pause here for more questions.
Sir, I mean, just making sure, since you didn't say this explicitly, the A parameter is not allowed to be 0, right?
Yeah, sorry. Yes, it's important. A, B are constants and A not equal to 0. That's important. Yes. Okay. Okay. So all of this discussion, this preceding discussion just now about affine connection and so on, all of this is true for any manifold with any connection on that manifold, right? It doesn't have to be a metric connection. Okay. So now we'll go specifically to the case of metric spaces. Okay, and let's talk about geodesics on metric spaces. So let's look at a manifold M with a metric G, and this metric G is some 0 to tensor. Okay, and now we will choose a connection which is a metric compatible connection. Okay, so what do we mean by this? So supposing we have some curve over here which will denote as C. Okay, so this is some curve C, and there are two vectors, let's say U and W. Okay, at some point P, and V is the tangent vector to the curve at this point. Okay, now by definition, what we meant by a metric compatible connection is that under parallel transport, the inner product of U and W, okay, that is GUW, which I can also denote as UW with angular brackets. Okay. Remember that you can't take this inner product unless you have a metric, right? There's no way to define such an inner product unless you have a metric. Okay. So if you take this inner product, okay, using this metric, then this inner product is conserved under parallel transport. Okay, that's how we define what we mean by a metric compatible connection. Okay, so in other words, as an equation, what we can say is the change along the v direction, okay, along the tangent vector to the curve of this inner product, which is GUW, is 0. Okay, so if I parallelly transport U and W, okay, that is by definition, when two vectors are parallelly transported, then del VU is 0 and del VW is 0. Okay, this is what we mean by definition of what it means to parallelly transport a vector. Okay, okay, so now, okay, if we take this definition, okay, then what we've seen in the last class is that this implies that del V of G is 0. Okay, that is, if I take the derivative along the V direction of the metric tensor G, then that is 0. This defines for me what I mean by my metric connection. Okay, because this, to define this derivative, okay, I need to define a connection on the manifold which allows me to compare vectors or tensors, okay, in particular 0 to tensors at different points on the manifold. So this is the statement that the metric is unchanged under parallel transport. Okay, and this defines a notion of a metric compatible connection. Okay, and we showed that if you choose a torsion-free metric compatible connection, then there's a unique choice. Okay, which was those Christoffel symbols that we wrote down last time. Okay, so now let's take a curve, okay, and let's take this curve to be a geodesic, okay, on a metric space. Okay, and let us assume two things. Okay, so first let us assume that our geodesic has an affine parameterization. Okay, that is, we're working in a parameterization where the tangent vectors to the geodesic satisfy del V is 0. Okay, so if V is some tangent vector to the curve, del V is 0. The second thing that we'll do is we'll assume that the connection that we're using on the to parallel transport along this curve is the metric compatible connection. Okay, so that is, we are assuming that this quantity del v acting on the inner product, this is equal to 0. So by definition, you can check easily. So this derivative acts linearly. Okay, so by applying the Leibniz rule, it acts first on g, then it acts on v, and then it acts on the other v. Okay, and now each of these is individually 0. Okay, so so these are 0 because by definition our geodesics satisfy this equation. Okay, we're assuming we're working in an affine parameterization. So both these terms are individually 0. And this term is 0 because we chose a metric compatible connection. Okay, we chose a metric compatible connection, so that leads to del Vg is 0. Okay, so okay, so now the important point is that that if you choose this metric compatible connection and you have an affine connection, then the inner product of the tangent vectors is unchanged under parallel transport. Okay, that is, the inner product is a constant along the geodesic. Okay, so everywhere along the geodesic, the inner product is unchanged. Okay, because the vectors themselves are unchanged under parallel transport. The tangent vectors are unchanged under parallel transport. And the inner product of these vectors is also unchanged under parallel transport. Okay, that means that this inner product itself is a constant along the entire geodesic. Okay, so this inner product of the tangent vectors, okay, being constant along the curve, okay, is not true in general for a non-affine parameterization. Okay, this relied crucially in the fact that we had an affine parameterization. However, even if you had a non-affine parameterization for the geodesic, okay, even if you had a non-affine parameterization, the sign of this inner product, GVV, will still be a constant even with a non-affine parameterization, as long as your non-affine parameter, okay, is a strictly monotonic function of your affine parameter. Okay, that is, if I reparameterize, okay, as some function of my affine parameter. So let's say in terms of my affine parameter, okay, when I say that GVV is, let's say, positive, okay, so suppose I choose it to be positive without loss of generality. Okay, so then what I'm saying is in components, okay, G mu nu dx mu d lambda, this is with the affine parameter, dx mu d lambda, this is positive. Okay, that's what we mean when we say this. Okay, in components. Now supposing we parameterize using the non-affine parameter. Okay, so suppose we parameterize using a non-affine parameter, then G mu nu dx mu d lambda times dx nu d lambda. Okay, so I can apply the chain rule, and I can write this d lambda with respect to the non-affine parameter as d lambda affine times d lambda non-affine by d lambda affine. Okay, and I'll get two factors of this, one for each of these terms. So what I have is my original inner product of the tangent vectors times some extra factor. Okay, and as long as d lambda non-affine by d lambda affine is monotonic, so let's say it's positive. Okay, that is, the non-affine parameter increases strictly monotonically as a function of lambda affine. Okay, then this is also positive. Okay, so that is, with my new parameterization, with my non-affine parameterization, okay, the inner product of the tangent vectors is positive if I started with my affine parameterization and the inner product of the tangent vectors was positive. Okay, so even if I use a non-affine parameterization, okay, so with my non-affine parameterization, then my inner product of these tangent vectors is not a constant. Okay, it's not a constant, but the sign of the of this inner product, that is still a constant, whether it's positive or negative or 0. Okay, is always going to be constant along a geodesic. Okay, so the implication, what is the implication of this? Okay, so this turns out to be a very important result, because what it tells you is that if suppose I have a pseudo-Riemannian metric G, okay, on a pseudo-Riemannian manifold, okay, the inner product of two vectors can be positive, it can be negative, it can be 0. Okay, so if it's positive at one point, okay, on a geodesic. So you have a geodesic on a pseudo-Riemannian manifold, okay, and at some point on this geodesic, this GVV is greater than 0. Then everywhere on the geodesic, GVV has to be greater than 0. Okay, and this doesn't care about what parameterization you use. So the tangent vectors, okay, the tangent vectors V prime are always going to be space-like, okay, everywhere along such a geodesic. Okay, and so you call such a geodesic of this type is called a space-like geodesic. Okay, on a Riemannian manifold, well, there's only one choice of the sign, right? The sign is always positive. Okay, but on a pseudo-Riemannian manifold, this GVV can be less than 0, and if I have a geodesic with GVV less than 0, then everywhere on if I at one point the tangent vector has negative norm, then everywhere on the geodesic the tangent vector will have negative norm. So the tangent vectors will always be time-like along such a geodesic, and this type of geodesic where the norm of VV is negative, those are called time-like geodesics. Okay, so such a geodesic is called time-like. And it's also possible on a pseudo-Riemannian manifold to have 0 norm. Okay, so if the norm is 0 at one point, okay, if V has 0 norm, V can be non-zero. Okay, V can be a non-zero vector with 0 norm. Okay, this is the critical thing about pseudo-Riemannian manifolds. So if the tangent vector has 0 norm at one point along the geodesic, at every point along the geodesic, it will have 0 norm. Okay, so if the tangent vectors are null everywhere along the geodesic, then you call the geodesic a null geodesic. So geodesics come in 3 types on a pseudo-Riemannian manifold. Either they're space-like, or they're time-like, or they're null. Okay, but on a pseudo-Riemannian manifold, the geodesics are always of one type. They cannot transition between space-like and time-like, or space-like and null, and so on. You worked out a specific example of this on the midsem where you used this metric, okay, the special Lorentzian metric. But this is true in general for arbitrary metrics as long as the metric is pseudo-Riemannian. Okay, what that means is that the eigenvalues of G have 1 negative value and 3 positive values. Okay, okay, but it doesn't mean that G can necessarily be put in this form everywhere on the manifold simultaneously. Okay, so this was a very specific case in which you had worked it out. The result is much more general, that you will always have either space-like geodesics or time-like geodesics or null geodesics, but geodesics are never switching between types of being either space-like or time-like or time-like and null. Okay, any questions here? Okay. Okay, now let's come to something something new. Okay, so one interesting thing that you can do is you can now define the arc length along a geodesic. Okay, you can define the length that you traverse, okay, as you move along a geodesic, and the length that you traverse along this geodesic. So first we'll define such a notion of an arc length. The second thing that we'll do is we'll show that this arc length, okay, that is, suppose I travel from here to here, okay, there's some arc length that I travel. That arc length itself can give you a parameterization of the curve, okay, and that arc length along a geodesic is an affine parameter. Okay, so this is something that we will show. Okay, so again we'll start. So we're starting with a manifold with a metric. So this is a metric space. Okay, and let's start with a simple case where G is a Riemannian manifold. Okay, so you can think about some of the examples that we did, like R2 with a Euclidean metric, or a sphere embedded in R3. Okay, these are examples of Riemannian manifolds. Okay, so we define the arc length S, okay, as the integral along the curve. Okay, so as I go from one point on the curve to another, from A to B, along the curve, okay, it's the integral of smaller pieces of this arc length. Okay, it's smaller pieces of this arc length. And what is the arc length? The arc length for a small displacement, okay, is the length that I travel. And the length that you travel, we've already decided that this length, once you have a metric, is given by this quantity. Okay, where these are displacements. Okay, and these are displacements along the curve. Okay, so if this is the displacement, and if I'm on a Riemannian manifold, this is a positive quantity. Okay, and I take this to be, so I take ds to be the square root of this quantity. Okay, so I've written ds as the square root of this quantity. Okay, g mu nu dx mu dx nu. So this is true in general on any Riemannian manifold. This could be true on R2 or on S2. Okay, and now what you can do is this curve itself you can parameterize by, let's say, some affine parameter. Okay, so let's say you choose some affine parameter alpha. So I can write this now using that affine parameter alpha. I can write it as dx mu by d alpha, dx nu by d alpha, and then I can pull out a d alpha over here. Okay, so this g mu nu is a function of where I am on the manifold. Okay, so as I'm moving along the manifold, at some point along the curve, okay, there's a parameter alpha, which is an affine parameter, which tells me where I am along this curve. And at that point, I have some coordinates x mu, which are parameterized, which depend on this parameter alpha. Okay, and by definition, we've chosen alpha to be an affine parameter, which means x mu of alpha satisfies the canonical form of the geodesic equation. Now, if we take this x mu of alpha, okay, and we also evaluate the metric coefficients at this point, g mu nu at this x, where these x's are functions of the alpha. Okay, so this is a function of x, which is a function of alpha. This is dx mu d alpha. Okay, so I can always differentiate this with respect to alpha. Okay, and so I can evaluate this at every point alpha, okay, along my parameterization or along my curve. Okay, where alpha is some affine parameterization. Now, this quantity right here, okay, is nothing but the inner product of v with itself, where v is the tangent vector. Okay, because dx mu d alpha is just the tangent vector in the affine parameterization. So this quantity is just square root of gvv times d alpha. Okay. Now along the curve, okay, we've already discussed this, but basically this inner product doesn't change as I move along the curve. Okay, the inner product of the tangent vectors does not change as I move along the curve. So for every point alpha, okay, if I change alpha from here to this alpha prime to alpha double prime, this inner product doesn't change. It's a constant along the curve. This is a constant along the curve if alpha is an affine parameter. Okay, if alpha is an affine parameter, then this is a constant along the curve. Okay, so now I pull out this GVV from the integral because it doesn't depend on what alpha I'm at along this curve. Okay, sorry, the square root of GVV. And so now what I have is just the integral of d alpha along the curve, which is the affine parameter. Okay, and the integral of alpha along the curve, okay, is just going to be some the change in alpha plus which is like, let's say, the alpha value plus some constant which depends on the initial value of alpha that I start with. Okay, so for example, if I start here and I define alpha is equal to some alpha naught, okay, this initial value of this integral, okay, is from up till from alpha naught to alpha. Okay, so what I get at the end is that the arc length S, okay, this is the arc length, is just equal to, okay, some constant along the curve. Okay, this constant is the norm of the tangent vector times an affine parameter plus a constant. Okay, or in other words, the arc length is related to the affine parameter in this way, where a and b are constants. Okay, and a is a non-zero constant because we assume that we're talking, let's say, on a Riemannian manifold. Okay, where this is a positive quantity. Okay, for non-zero tangent vectors. So, so now what we have is, if alpha is an affine parameter, what we've already seen is this kind of reparameterization is an affine reparameterization, and therefore S is also an affine parameter. Okay, so now if I have a curve, okay, if I have a curve on a manifold, we know at least one affine parameter that can describe the core, where I am along this curve. I can describe it in terms of the arc length that I've traveled to get from one point to another. Okay, that gives me a parameterization for this curve. and that's an affine parameterization. So if I go from here to here, I can calculate a length that I travel once I have a metric. Once I calculate that length itself becomes an affine parameter that I can use, okay, to tell me where I am along this curve. Okay, now let me just mention two important points about this affine parameter, which is the arc length. Okay, so the first thing is we've seen that we can write S in this way. Okay, S was actually the square root of g mu nu dx nu integrated along the curve. Okay, where dx mu and dx nu are some small displacements. But I don't have to parameterize the curve using an affine parameter. I could use a non-affine parameter. So I could define by some d lambda and put a d lambda here. Okay, so I could write it this way, where lambda is a non-affine parameter. Okay, so lambda is not an affine parameter in this case. In this case, however, this quantity, the square root of g mu nu times dx mu d lambda dx nu d lambda, this is the norm of V. Okay. The norm of the tangent vectors when I have a non-affine parameterization for the curve. If I'm choosing a non-affine parameterization, then this product, this inner product of V is not a constant anymore along the curve. Okay, so you can't pull it outside the integral in that case. Okay, so you can no longer pull this outside the integral. However, the parameter S is still an affine parameter. We've already proved that S is an affine parameter. Okay, so S is an affine parameter, but you can write it in this way in terms of the arc length, okay, with a non-affine parameterization. Okay, so this arc length itself is independent of the choice of parameter that you use. Okay, independent of this choice of parameter lambda. So we say that this arc length itself is reparameterization invariant. Okay, if you evaluate it in this manner, okay, using arbitrary curves, the arc length that you calculate does not depend on the parameterization that you use to calculate it. Okay, this arc length exists independently of that parameterization. Okay, that's the first point. Secondly, now if you have a pseudo-Riemannian metric on which the tangent vectors can be either space-like or time-like or null, okay, along a curve, you can define, suppose my curve is a time-like curve, that is the tangent vectors are always, suppose the tangent vectors are always negative, okay, along this curve. Then I can define that arc length along a time-like curve by using a minus sign here, because this inner product is negative, okay, for a time-like curve. And now we can put a minus sign here, and now this is a positive quantity. And I can define the arc length as this quantity, okay? It's the square root of this positive number. That's what I define by the arc length, okay, times d lambda, that is the arc length, okay, along the curve. So this is the generalization of the notion of arc length to pseudo-Riemannian manifolds along a time-like curve, okay? So this gives me an arc length along a time-like curve. That's why I put the subscript t here. Okay, and this is a real number. Okay, this is a real number because this number is positive. Okay, the whole thing with the minus sign. So this gives me the real arc length along a time-like geodesic. Okay, this gives me the arc length along a time-like geodesic. And now similarly, I can do this for a space-like geodesic. Okay, so on a space-like geodesic, okay, what I have is this. Okay, SS is equal to square root of g mu nu dx mu d lambda dx nu d lambda, but now with a plus sign here. Okay, because this quantity is positive for a space-like curve. Okay, so if my curve C is space-like, the arc length along this space-like curve, okay, has a plus sign over here. Okay, so if this is a real arc length along a space-like geodesic. Okay, any questions at this point?
Sir, apart from the physics interpretation, are there any missing pieces now that, I mean, in the midsem you had made the remark that the proper time is a parameter that will always make your geodesics, basically that it's an affine parameter. So is basically this the justification, or are we missing?
Yeah, this is the justification. So thanks for bringing that up. So, okay, so now if we look at on a general pseudo-Riemannian manifold, okay, sorry, this is what we had, right? So on a general pseudo-Riemannian manifold, we had argued that along a time-like curve, okay, what we just argued is along a time-like curve, I can define the arc length as this quantity. Okay, and this arc length is an affine parameter. Okay, or when I integrate this, I get an affine parameter. Okay, this you can see now, this quantity that we're calculating here, this is exactly what on, let's say on your if I take a general path through Minkowski spacetime, for example. Okay, so sorry, this is Minkowski spacetime. Okay, so imagine some time-like curve. Okay, so a time-like curve would be one where dx by dt, okay, is always less than c, okay, or 1 in units where c is 1. Okay, that defines a time-like curve, but it can have changing velocities. Okay, so you can have a curve which is, let's say, starts out like this, then goes like this, then like this, and like this, but always careful that the tangents to this curve never exceed the speed of light. Okay, so dx by dt should never be greater than 1. Now, if you ensure that, okay, you have a time-like curve. Okay, and now what we're saying is, given that I start. Okay, so now first of all, what is this quantity? What is this arc length calculating? Okay, the arc length is calculating minus, and here we had eta mu nu. Okay, for a Minkowski spacetime, dx mu dx nu. Okay, that's what we were calculating. Now this quantity, okay, is nothing but square root of dt square minus dx square minus dy square minus dz square. Okay, and this, okay, is as long as I have a time-like interval between any 2 points, this is just exactly d tau square. Okay, or this is d tau. Okay, so the arc length along a time-like curve like this is just a measure of the proper time. So if you imagine that this is a particle following a time-like curve, okay, then d tau is then d tau is, or basically the arc length s is equal to tau up to some scaling. Okay, so basically the proper time of experienced by this particle, okay, the proper time experienced by this particle is exactly the affine parameter. I mean, it is an affine parameter along this time-like curve. Okay, sorry. So first of all, I have to specialize to geodesics, but on a geodesic, okay, it is so affine parameters only make sense when you talk about geodesics. Okay, along a general curve, okay, the arc length is the same as proper time. On a geodesic, okay, arc length is an affine parameter, and therefore proper time is also an affine parameter on a geodesic. Okay, so this was the statement which was not justified in the midsum, but this is the proof of it. Okay, and this is more general than just Minkowski space. This is true on arbitrary metrics, pseudo-Riemannian metric spaces. Okay, in particular, I'm thinking about Lorentzian metrics, which have signature minus, plus, 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 no matter how many spatial dimensions. Any more questions? Okay, so now we'll come to the probably one of the most interesting points about this. Okay, so on a metric space, so if you have a metric space M, so there's a manifold M with a metric G, and if you have the Levi-Civita connection, okay, then the geodesics are not just the straightest possible curves. Okay, that is, they're not just the curves where the tangent vector remains parallel to itself. They are also the shortest or maybe the longest possible curves which connect two different points. Okay, that is, geodesics extremize the arc length between any 2 points on the manifold. Okay, so let us prove this. Okay, so what we'll do is we'll take a pseudo-Riemannian manifold with any time-like curve C, which connects 2 points. So we'll take this point here, we'll call it P, and this point here, and we'll call it Q. Okay, and we have some parameter lambda. Okay, let's say it goes between 0 and 1. Doesn't really matter what the range is. And I mean, it can go beyond 0 and 1 also. Okay, but the point 0 corresponds to the point P, and the point 1, when lambda is equal to 1, you're at the point Q. Okay, and x mu of lambda is this curve. Okay, so in some coordinates, x mu of lambda tells me the coordinates along this curve. As I vary lambda, what is the x mu that corresponds to different points? So now if I want to calculate the arc length along this curve, the arc length along this curve, okay, is equal to, and let's assume that we're on a pseudo-Riemannian manifold, and let's assume that this is a time-like curve. Okay, then we can define the arc length in this way. Okay, it's minus g mu x dx mu d lambda dx mu d lambda times d lambda. Lambda may or may not be an affine parameter. Okay, in fact, we here at the moment we're just talking about arbitrary curves, not geodesics. Okay, so so it's not at all obvious. Okay, this is just the arc length along this arbitrary curve. Okay, so the notion of affine parameter only makes sense for a geodesic, right? Because it puts the geodesic equation in a particular form. Here we're not saying anything about geodesics. Here we're just saying we have an arbitrary curve S. Okay, where this is the arc length along the curve. Okay, this is a definition of arc length, and this curve has the properties that x mu at lambda is equal to 0 is the coordinates of the point P. Okay, and x mu at lambda is equal to 1 is the coordinates of the point Q. Okay, so the curve maybe extends beyond P and Q, but at 0 it's here, at 1 it's over here. Okay, these are arbitrary points, of course. Okay, in some particular parameterization, I'm at P when lambda is 0, and I'm at Q when lambda is 1. So lambda is just some parameter along the curve. Okay, so again, just to emphasize this, affine and non-affine, okay, is only defined for geodesics. Okay, for these general curves, there's no notion of what you mean by affine or non-affine. Affine is specific to geodesics when you put them a geodesic equation in a particular form. Okay, or you demand a condition on the geodesic. Now, when I take the points P and Q, there are many curves, okay, which I can draw, okay, through the points P and Q, such that at lambda is equal to 0, I'm at the point P, and lambda is equal to 1, I'm at the point Q. Okay, so this is one curve, this is one curve, and so on. So there are many curves that I can draw through P and Q. So many curves that satisfy these boundary conditions. Okay, and now this action, okay, is evaluated for different curves. Okay, this action is a function of different curves, or equivalently, sorry, not this action, this arc length is a function of different curves. Okay, this arc length is a function of different curves, and since this is a function of different curves, I can think of it as the curve itself is defined by x mu of lambda. So I can think of this as a functional of these functions. Okay, it depends on what these functions x mu of lambda are. Okay, so for every curve, I have a different choice of these functions x mu of lambda. And depending on which curve I choose, okay, I have a different arc length that I cover when I go from P to Q. Okay, so in this case, I cover this arc length. In this case, I cover this arc length. In this case, I cover this arc length. Okay, and you have to have a notion of how those arc lengths are measured. But for each curve, you can see that I will get a different arc length. Okay, and now the claim is that among all these possible curves, okay, there is one curve which is the geodesic. Okay, there's only one curve which is the geodesic, which passes through P and Q, and it's the shortest possible curve connecting P and Q. Okay, the shortest possible curve connecting P and Q is the geodesic. Okay, so the claim is, let me write that claim. It's either the shortest or the longest, okay, or the longest possible curve connecting P and Q is a geodesic. Okay, so we'll prove this now. Okay, so here I've just defined the arc length. Okay, and so now what I want to do is I want to find now what is the path. That is, I want to find the curve x mu of lambda. Okay, I want to find the x mu of lambda such that S is extremized. Either S is a maxima or a minima. Okay, so first let me find. Okay, so the strategy will be, okay, to prove this. Okay, the first thing we'll do is find the shortest / longest curve connecting P and Q. Okay, that's what we'll try to do. Okay, and in other words, what we're trying to do is we're trying to extremize the arc length. Okay, that is, S is a function of x mu of lambda, where x mu of lambda satisfies these boundary conditions. Okay, that it's some coordinates of some specific point P, and at when lambda is equal to 1, these are the coordinates of some other specific point Q. Okay, and we want to extremize this. Okay, that's the first thing that we'll do. We'll try to, so when we extremize it, we will get some particular solution, x mu lambda particular. Okay, we'll get some particular solution. Okay, maybe one, maybe more. Okay, we'll get some specific solutions. We won't have arbitrary curves anymore. Okay, and now once we find this, okay, we'll show that the particular solution that we find actually satisfies the geodesic equation. Okay, that is, it satisfies the equation d square x mu t lambda square plus gamma mu nu rho dx nu d lambda dx rho d lambda is 0. Okay, so this x mu of lambda satisfies this equation, where gamma is this metric connection. Okay, the one that we had written down earlier, that is, it's g mu sigma partial nu g sigma rho plus partial rho g nu sigma minus partial sigma g nu rho. Okay, so with this particular choice of metric connection, okay, we'll find that the x mu lambda that extremizes this path length satisfies this geodesic equation. Okay, so effectively what we're going to show, okay, is that the curves that so geodesics do two things. Okay, geodesics on a metric space do two different things. One is that they keep tangent vectors parallel to themselves, or they keep tangent vectors unchanged along themselves. Okay, as long as you're using an affine parameterization. And the second thing that they do is that they basically trace out the shortest or the longest possible path between 2 points on the manifold. Okay, so this is some interesting property of geodesics on a metric space. Okay, so let's see how we'd go about proving this. Okay, so the first thing we have to do is we have to find the shortest or the longest curve connecting P and Q. That is, we have to extremize this arc length, okay, as a function of x mu of lambda with these boundary conditions, okay, that x mu must satisfy. Okay, so the trick will be very simple. Okay, this is a problem that you might have seen before in a disguised form in classical mechanics. Okay, so the idea will be you treat S as an action. okay, and lambda as a time parameter of this action. Okay, so S is a function of a path x mu of lambda, where lambda is, you can think of as a time parameter. Okay, and the different x mu's are your different degrees of freedom that you have, different canonical coordinates, if you like. Okay, so this is like in classical mechanics, you might have studied something like this: q1t, q2t, q3t, q4t, right? Something like that. So that's what we're doing here. Okay, and your action is an integral of some Lagrangian dt. And similar, sorry, in classical mechanics, your action is a function of some Lagrangian, some L which depends on Q and Q dot dt. Okay, with some boundary conditions on Q at some T naught, you know the value, and Q TF, these are some fixed quantities. Okay, similarly, what we're doing, and the way you would find this, okay, is you'd find the Euler-Lagrange equations of motion. That is, for each degree of freedom. Okay, so for each degree of freedom, Q1, Q2, Q3, Q4, you'd write down an equation like this. You'd vary the action with respect to Qi as a function of t, and you'd set this to 0. And what this results in is your Euler-Lagrange equations. Okay, d by dt of partial L partial Qi dot minus partial L partial Qi is 0. Okay, and you have to impose these boundary conditions. Okay, and you solve this for Qi as a function of t. Okay, so that's exactly what we have to do here. Okay, so we have S as a function of x mu of lambda. Okay, we're saying that x mu at lambda is equal to 0 is fixed. Okay, x mu at lambda is equal to 1 is fixed, and S itself is equal to the integral, okay, of d lambda, so this is like your dt, times square root of minus g mu nu, okay, which is a function of x mu times dx mu d lambda dx nu d lambda. Okay, so this is your Lagrangian. Okay, so we have a Lagrangian, and this Lagrangian is square root of minus g mu nu of x mu, okay, dx mu d lambda dx nu d lambda. All right. Okay, so now you see that this Lagrangian depends on so this dx mu d lambda. Okay, this is exactly what I mean. This is like saying dq dt. Okay, this is like taking dq1 dt, let's say. Okay, or dqi dt. Okay, so this is nothing but what we call x mu dot. Okay, in this notation. Okay, where the derivative is with respect to lambda. Okay, so in shorthand we can write this as L is equal to square root minus g mu nu as a function of x mu. Okay, x mu dot x nu dot. Okay, now I just want to emphasize something to you just for practice with problems. Okay, I'm writing the x with a mu index, but secretly I should be very careful. Okay, this is just to remember that it's a function of arbitrary the x coordinates. Okay, I'm already using a mu coordinate here in this repeated summation. So just to be safe, I should avoid repeating the index here. Okay, because this index mu is not summed over. Okay, so if I really want to be very pedantic about this, I'll put an x row here. Okay, just to remember that this g mu nu is a function of my coordinate, and x mu is a specific mu which is summed over here. Okay, so if you like, there's a sum over mu nu here. Okay, which is going in, which we're obviously suppressing. So this is our Lagrangian, And the Euler-Lagrange equations of motion for this, okay, we can write as d partial L partial x mu dot dt minus partial L partial x mu is 0. Okay, how many Euler-Lagrange equations do you have?
Like n, if n is the dimension of the manifold.
Right, since mu runs from 1 through n, for every value of mu, where n is the dimension of the manifold, okay, because these are the coordinates of the manifold. Okay, so sorry, I shouldn't write d by dt, d by d lambda. Okay, so for every value of mu, you get one equation. So these are n equations, and you have these are n equations, and these are second order differential equations. Okay, they will turn out to be second order differential equations. Okay, and you have 2n initial conditions or 2n boundary conditions. Okay, which is exactly what you need to solve these equations. Okay, what are the 2n boundary conditions? You have all the x mu's at lambda is equal to 0. This is n boundary conditions. And you have all the x mu's at lambda is equal to 1. These are the other n boundary conditions. So you have exactly the number of equations and boundary conditions to solve these equations. Now, we won't actually solve them. We'll just look at the form of the equation, and we'll show that that form of that equation is exactly the geodesic equation. Okay, so we'll show that if x mu satisfies this equation, then x mu satisfies the geodesic equation. Okay, so that's what we're going to show next. Okay. Okay, so what we'll show is that that equation, okay, the equations of motion essentially are the same as the geodesic equations. Okay, except that it's not exactly true. Okay, that's the same as the geodesic equations. The equations look much more complicated when you write them with this, but the solutions to this equation are exactly the same as the solutions to the geodesic equation. Okay, so secretly they are the same set of equations. Okay, so the trick is to show that the set of equations that you get from extremizing the action is exactly the same as those that you get from the geodesic equation with the metric connection. Okay, so we'll just since we have some time, let's work it out. Okay. Okay, so I was going to give this as a homework problem, but since we have some time, we'll work this out. Okay, let me just say the main point. Okay, so what we'll show is that basically the solutions to this equation, okay, are exactly the same as the solutions to the geodesic equation with this metric connection. Okay, the geodesic equation was proved under the assumption that the tangent vectors to a curve don't change. That is, basically we said that geodesics are the straightest possible curves. Straightest possible curves given a particular connection, and that connection was the unique metric torsion-free metric connection. So now what we're saying is that the solutions which extremize the arc length, okay, between 2 points on the curve, those solutions are exactly the same as what you would get from the geodesic equation. Okay, so geodesics actually do two things. They are on a metric space, they are both the straightest possible curves as well as the shortest or longest curves. That is, they extremize the arc length along a curve. Okay. Okay, so since we have a little time, let me just actually work this out for you. Okay, so we'll work out the Euler-Lagrange equations for this Lagrangian. Okay, so let me just copy this. Oops. where we had L is equal to minus G mu nu x. Okay, I'll just drop the index on the x. Dx mu d lambda dx nu, or sorry, x mu dot x nu dot. Okay, so instead of working out this, okay, what we'll show is two things. So first is we'll choose the parameter lambda to be the arc length. Okay, so for an arbitrary curve, we can parameterize it in many different ways. Okay, one choice of parameterization is to choose lambda to be the arc length along the curve. Okay, so this is a generic choice. Okay, again, this is not an affine parameterization because these are arbitrary curves. These are not geodesics. So the notion of affine doesn't make sense. Okay, so lambda is just the arc length along the curve. Okay, we can choose to parameterize the curve using the arc length. Okay. So you're perfectly free to do that. Okay, so one is we'll choose lambda to be the arc length. Okay, when we parameterize these curves. The second thing that we'll do, okay, is that rather than working with this Lagrangian, okay, we will actually work with a modified Lagrangian f. Okay, so we'll work with this modified Lagrangian f, and with this modified Lagrangian will be this. It'll be minus half g mu nu Okay, so this is not the same as the original Lagrangian. This doesn't have a square root and it has a extra factor of half over here. So this modified Lagrangian f is equal to L square by 2. Okay, so this is a modified Lagrangian. Okay, and now what we can argue is that the action, okay, we'll call this a new action, okay, as a function of x mu lambda. The modified action, okay, with using this new Lagrangian f. Okay, what we'll argue is that the Euler-Lagrange equations for this action for S prime, okay, are exactly the same as those for the original action S when we use the arc length as the parameter. Okay, so let's see how that is. Okay, so if we use S prime, okay, then the Euler-Lagrange equations of motion are just this: d by d lambda of partial f partial x mu dot minus partial f partial x mu, okay, is equal to 0. Okay, so these are the Euler-Lagrange equations over here. Okay, but now what we can do is we can just ask, okay, suppose we just took, okay, d by d lambda partial f partial x mu dot minus partial f. Okay, so these are S prime equations of motion. Okay, but now let's calculate this. Okay, and we won't apply the equations of motion that we get from S prime, but we'll just calculate the left-hand side of this. Okay, using the equations of motion of the original action. Okay, use two things. One is you use the fact that F is equal to L square by 2. And second is you use the equations of motion that L satisfies. Okay, and L satisfies d by dt, d by d lambda. Okay, of what was it? D by d lambda of partial L partial x mu dot minus partial L partial x mu is 0. So we'll use these two things. Okay, so let's work it out using these two things. So the left hand side is this partial f partial x mu dot. We can now write as using f is equal to L square by 2. Okay, we can write this as L times partial L partial x mu dot minus L times partial L partial x mu. Okay, which I can further simplify as L times d by d lambda plus there's an extra piece here now, which is dl d lambda times partial L partial x mu dot. Okay. Okay, now by the Euler-Lagrange equations for L, okay, this is 0. Okay, so what we have is that this is partial L partial x mu dot dl d lambda. Okay, however, if you remember what L was the square root of minus g mu nu dx mu d lambda dx nu d lambda. Yeah, okay, I didn't show this properly, but okay, so this is L. Okay, now see, the point is that this L, okay, is the arc length along the curve. Sorry, this is not the arc length. This L is the norm of the tangent vector to the curve. Okay, it's this. Yeah, what I want to argue is that for a general curve, okay, not necessarily a geodesic, if I parameterize the curve using the arc length, okay, then the norm of the vector, okay, does not change along the curve. Okay, the norm of the tangent vectors does not change along the curve. So this is not just true for geodesics. So now if I have an arbitrary curve, okay, and I use the arc length as a parameter along the curve. Okay, so when I choose the arc length, that fixes the tangent vectors, okay, as this. And if I choose the arc length as a parameter, then the norm, okay, so these are the coefficients v mu. So the norm g mu, v mu, v nu, okay, of the tangent vectors, this does not change along the curve. Okay, that is dl by ds. As I move along the curve, this quantity remains unchanged. Okay, so we'll prove this statement in a second. Okay, that for an arbitrary curve, if I use the arc length as a parameter, the norm of the tangent vector does not change. Okay, so but if we assume that that is true, okay, then dl by d lambda or dl by ds, since we're using lambda as the arc length along this curve, this is 0. So what we just proved is that this quantity, okay, by using the Euler-Lagrange equations for L rather than for F, that gives us 0. Okay, so what that means is whether you use the action of S prime or whether you use the action S, okay, you end up getting exactly the same equations of motion. Okay, you end up getting exactly the same equations of motion. Now let's work out what this equation of motion is. So it's more convenient to work with F because F doesn't have these square roots in it. Okay, so let's work with this and work out the equations of motion. Okay, so what we have is d by d lambda of partial f partial x mu dot minus partial f partial x mu is 0, where f is equal to minus half g mu nu of x partial, sorry, x mu dot x mu dot. Okay, so this is f. So now I can plug this in here. Okay, this you see, basically this is like your in your typical Lagrangian. This is like your standard Lagrangian. Okay, qi dot qj dot. If this was delta ij, okay, it would be like your standard Lagrangian. Okay, which is like half q1 dot square plus q2 dot square plus so on. Okay, the difference is that now the coefficients, okay, can depend on x. Okay, this g mu can depend on x. Okay, so instead of this, I now have some coefficients which depend on q. Okay, g I j. Okay, so let's plug this in. Okay, to these equations of motion. And what we get is, so the first term only differentiates the derivatives, okay, x dots, okay. So what we get, and since g is symmetric, okay, it doesn't matter whether we act on this or on this, okay, we'll get the same thing. So we'll write it as g mu okay, x mu double dot, okay. Okay, and there's a minus sign here, and now this minus sign and there's an extra minus sign will give you a plus sign. Okay, and now this is a derivative of g mu nu with respect to x mu. Okay, so that's partial. Sorry, I should have been very, very careful here. So supposing I'm differentiating with respect to a mu coordinate, okay, what it does is, let's say, I should really think of this as a dummy coordinate, okay, sigma. When sigma is equal to mu, I will differentiate this. When sigma is equal to nu, I will differentiate this. Okay, so because really you should think of this as there's a summation over mu nu here. Okay, so I'm just working this out explicitly. It may be obvious to you, but if you don't have that much practice with indices, it's good to work this out in detail. Okay, so so when I differentiate this with respect to x dot sigma, okay, what that gives me is it gives me a delta mu sigma, okay, g mu nu x dot nu, and then there's a d by d lambda. And now when I differentiate this with respect to x dot sigma, I get a delta mu nu. Sorry, I get a delta sigma nu, a delta nu sigma g mu nu x dot mu. Okay, and this whole thing is differentiated with respect to lambda. And now this term over here, okay, and sorry, and then there's a minus sign, and then there's a factor of half. Okay, from here. And now this term over here will give me a plus half. And then I differentiate this with respect to x, okay? The differentiation with respect to x doesn't affect these x dots, it only differentiates this. So I get a plus half partial sigma g mu nu, okay, of x mu dot, x mu dot. Okay, so it's important to be very careful when doing this kind of differentiation with indices. Be careful about which ones are summed over, which ones are not summed over, which ones are free indices with respect to which you're differentiating. Okay, it's very, very important to keep track of this, otherwise you'll get thoroughly confused, as I almost did just over here. Okay, so okay, so now if I want to simplify this further, okay, I will. So now you apply this in the summation. Okay, so this delta mu sigma g mu nu will just so if there's a summation over mu here implicitly, what this does is, since there's a delta mu sigma, that will just give me a g sigma nu x dot nu, and this will give me a g mu sigma x dot mu. Okay, and then there's a d by d lambda here. Okay, and there's a minus half. And I have a plus half partial sigma g mu nu x. Oops. Okay, which I'll write as this. Okay, so we'll just simplify a little bit more. So this d by d lambda, okay, I can now write as so I can differentiate the x dots. Okay, and this whole thing. Now, okay, I can replace this dummy index nu by mu, and I can exchange the sigma and mu since G is symmetric. Okay, so I can write this as mu sigma. So these are the same term. Okay, and so now when there's a factor of 2 which cancels with this factor of 2, so I get minus d by d lambda of G mu sigma x dot mu. Okay, plus half partial sigma G mu nu x mu dot x nu dot equals 0. Yeah, and now I need to simplify further. Okay, so the simplification further is this d by d lambda can act on the x mu dot, in which case I will get minus G mu sigma x mu double dot. Okay, or it can act on the G mu sigma itself. Okay, and I'll use the chain rule and I'll write d by d lambda is equal to is equal to dx mu d lambda partial dx rho d lambda partial x rho. Okay, so if I plug this in here now, I will differentiate this with respect to x mu dot times dx rho d lambda. Okay, partial rho g mu sigma. Okay, and then plus this other term. Plus partial sigma g mu nu x mu dot x nu dot with factor of half. Okay, this is equal to 0. Okay, and then we'll simplify further. G mu sigma x mu double dot. And I'll write this term out as two different terms now. Plus half. Yeah, so this is x rho, this term is x rho dot. Okay, so I'll write it as partial rho g mu sigma times x rho dot times x mu dot. Okay, and I can also write this, so I'll split it into two different terms, which I'll write like this, and I can also write, I can change the dummy indices rho and mu, and I can write it as this. And finally, I have this term. Okay, and here again, I can replace the dummy index nu by rho. Okay, and there's a minus sign, a relative minus sign here. Minus partial sigma g rho g mu rho, sorry. G mu rho x rho dot x mu dot. Okay, and Now finally I can invert this matrix G mu sigma, and I can write all of this as x mu double dot is d square x mu d lambda square, okay, plus half, and now I've inverted this G, so what I will get is G mu sigma times partial rho G mu sigma plus partial mu G rho sigma minus partial sigma G mu rho times x rho dot x mu dot equal to 0. Okay, and this finally gives me d square x mu d lambda square plus gamma mu rho sigma. Oh, I messed up somewhere. Yeah, I repeated the index mu. Okay. I repeated the index mu. I should have called this nu here. Dx nu. Okay, I get this equation where gamma nu rho sigma is the metric connection, okay, or the Christoffel symbol. Okay, so in other words, what we did is, let's just recap what we did. We extremized the action. Okay, we extremized the action for the arc length. Okay, we extremized this arc length. When we extremized this arc length, we found that the equations of motion that we got, okay, are exactly the same as the equations of motion that we would have got if we instead use this different action. Okay, that is the action for F, which is L squared by 2. So what we did instead was we worked out the equations of motion for F. Okay, and we worked out the equations of motion for F. The equations of motion that we got in that case, okay, which basically is the curve. So when I solve this for x mu of lambda, this gives me the curve that extremizes the path length, okay, or the arc length. Coincidentally, this turns out to be exactly the same as the geodesic equation, okay, which keeps tangent vectors unchanged along a curve. Okay, so what this tells you is that geodesics are basically both the straightest curves, that is, they keep tangent vectors unchanged, as well as they give you the shortest or longest distance along a curve. Okay, so if you did the assignment or you're still doing it, okay, on a two sphere, okay, you can show that the geodesic, if I take 2 points, okay, so for example, if I take any 2 points here, okay, the shortest distance will be this. Okay, it's the great circle or like a longitude which connects these 2 points. And for example, if I want to find the any arbitrary 2 points, okay, on a circle, I can always imagine, sorry, on the sphere, I can always imagine rotating the sphere such that one of the points is the North Pole. Okay, and then the other point, the shortest way to connect from this point to the North Pole is always to move along a longitude. Okay, that is the straightest possible line, and it also turns out to be the shortest possible line to get from here to here. Okay, but the geodesic equation doesn't actually tell you whether it's the shortest or the longest. You could have taken this, but the same differential equation, depending on which way you take your parameter lambda to be, right, you might end up going in the opposite direction, and you might end up covering the longest path to get from here to here. Okay, so the distance can be either the shortest distance or the longest distance. The geodesic doesn't tell you which, it just extremizes the arc length. This has the smallest arc length, okay, and this has the longest. Both of them are solutions to the geodesic equation. Okay, so there's only one step which we didn't work out. Maybe I'll give it as a homework. I should have probably worked it out before, but which was to basically argue that for an arbitrary curve, using the arc length as a parameter, then the vectors, the tangent vectors, the norm of the tangent vectors is basically unchanged along the curve. Okay, so this maybe you can try out as a homework exercise, or I'll try to work it out myself also. Okay, yeah, questions, Khagesh?
Sir, is there a method in which we can identify which geodesic is the shorter one or the longest? Like we have extremums. How do we know which is the maximum one and which is the?
Well, technically, what you should compute is the second derivative of this. So you have to calculate this kind of thing. Okay. So there's a way to do this using functional calculus. But another simple way to do it is if I solve the geodesic equation, let me just actually calculate the arc lengths, right? Along, I mean, I'll get two solutions. Let me calculate the arc lengths along each of the solutions. Right. In this case, I'll get two solutions. I mean, in general, you could have many more solutions. But you calculate this arc length explicitly, you calculate this arc length explicitly and compare them. If you want a generic procedure that works, you actually should compute this kind of quantity. Okay, it's like computing a second derivative of S along different paths. And you compute the eigenvalues of this. If this is positive, so all the eigenvalues are positive, then it's a minimum. If all the eigenvalues are negative, it's a maximum. Okay, if all strictly less than. And if some eigenvalues are positive and some are negative, then it's a saddle. Sorry, the Kagesh, can you, sorry, Kagesh, you're muted. Devashish, I can't hear you clearly.
Can you hear me now?
It's a bit faint, but go ahead. Sorry, just cannot hear you.
Sir, I type it in the chat.
Yeah, okay. Any other questions till then? Okay, so the question that Devashish asked is, this path, the longest path, isn't this a saddle? It's not actually the longest path connecting the 2 points.
I mean, in general, you could just go in circles and circles around the sphere, and
You mean something like this
is
longer, like with arbitrary number of. Is that what you mean?
Yes, sir.
Yeah, I think that's right. Okay, so maybe this is not. Yeah, this is probably I mean, it's a saddle.
Sir, in fact, I think the thing is that there is no longest path, so there's no contradiction.
There is no longest path. That is true. Actually, sorry, this is not a saddle. It's actually a local minimum. Okay, of the this is a local minimum. Any deformation of this path, any small deformation of this path will give a longer path. So these are both local minima of the path length. Okay, this is the global minima. This is a local minima. Right, and a procedure for finding this is of course it doesn't tell us whether it's a global or a local minima, and there's no local prescription of calculating something like this which can tell you whether it's a local or a global minima. Right, you have to check all the minima, and you have to calculate the arc lengths along all those minima.
Hello, sir.
Yeah.
Sir, in this proof, like while deriving, like why are we getting 0 on the right hand side for the geodesic equation? Like the general form has a non-zero term.
Well, because we started by using lambda as the arc length along the curve. Right, that was our starting point. So we chose lambda to be the arc length. When we chose lambda to be the arc length, it's only then that these two Lagrangians are actually give you the same equivalent action equations of motion. Right, that was critical. That lambda is the arc length, because when lambda is the arc length, then we are well, we didn't prove it, but basically dl by d lambda will be 0. Okay, which is where L was this quantity. Okay, which is basically the norm of a vector along the general curve, the norm of the tangent vector. Okay, that doesn't change along the curve. So it was critical that only when the arc length is chosen as a parameter, this is true. And therefore, it's not surprising that the equation of motion that we get is the equation of motion for a geodesic where the arc length is used as the parameter along the curve, which is basically the affine geodesic equation.
Yeah, okay, sir.
I mean, of course, the final answer doesn't depend on your parameterization. We proved it using a particular parameterization. Okay, because the arc length doesn't depend on your parameterization, right? That's what we already argued. Okay. Yeah, go ahead.
So could you just move a little bit above, like the step before this, where you multiplied with the inverse of the G mu sigma? Yes, sir.
Yeah. So let me be clear what I did here, right? I took G sigma nu, okay, and this is what I multiplied by. Okay. So what this is the inverse metric. Okay. So I multiplied and I summed over sigma. Okay. So sigma is a free index here. So when I did this by definition, since this is the inverse metric, it gives me delta nu mu, and over here I get this G nu sigma.
Yes, sir. It's clear now.
These are all, tiny little steps, but it's really important that you practice them, especially if you're not used to this, right, or this kind of index notation. And it only comes by doing problems. Okay, so try to do as many problems as you can. I'll try to give you more assignment problems for this practice. And even the assignment till now and the mid-sem problems, they're all about practicing the same ideas over and over again. Okay, thanks. So we'll stop here and we'll meet on Thursday. Okay, good night.